Hello YouTube. Today we're going to work on some application of double derivatives. So we're just going to give a more applicable type of problem that you'll need to use double derivatives for. So here's the example. The amount of rainfall per year in the triangle area or triangular area bounded by 1, 0, 5, 0, and 5, 4 is given by the function 4 over x times the quantity y plus 1 inches. Find the total amount of rainfall for the year. Okay, so we're going to find the total amount of something over a given amount of time. We will need to use integration. To do that, first let's sketch out the boundary. So I plot all the points, and since we know it's a triangular region, all you gotta do is connect the dots, just like in first grade, right? Okay, so I drew the triangle, and I also drew what the lines here represent as a function. But first we gotta figure out what this line would be. Let's see. If you calculate the slope, you should get y equals x minus 1. Alright, so there's that. And remember, since we're integrating, we're going to be adding up an infinite number of things, and those things, in this case, are rectangles. And we'll just say that is R for rectangles. Okay, so real quick, the R we're using for vertical rectangles. So keep that in mind. That's important. That's just the way I chose to do the problem because there's many different ways you can do it. dy dx, dx dy. So I'm doing the vertical way. So since I'm doing it the vertical way, that means we're going to have dy dx. And to remember that, I guess, dx, the one that's on the outside, is how you would normally integrate. With dx, you're normally doing vertical rectangles. So that's how you can remember what's on the outside is the way that you're integrating, how you chose to integrate. Okay, so remember, since double integrals represents the volume, and that is the key here. We are trying to find the volume of rainfall over the given year in that region. So first thing to do is kind of split off this region here, and you know that this is going to be y equals, and this will be x equals some number. And just a key here, generally what's on the inside are usually going to be numbers and a function or two functions, and what's on the outside you're just going to have numbers. The reason for that is because you want to get a solid number or volume or whatever at the end. If you had functions everywhere, then you would just get your area and functions, and that would just be pointless. So let's evaluate this here, figure out our limits of integration. So if we're integrating in this direction, we have to do top minus bottom. So what does the rectangle hit first at the top? That would be y equals x minus 1, and what's at the bottom? Y equals 0. So that'll be our inside limit of integration here. There you go. So remember, it's top minus bottom, and that's how we knew that. Okay, so now we're going to figure out how high we're going for our second limit of integration. That'll be from, let's see, actually, yeah, 0 to 5, right? So yeah, 0 to 5, 0 to 5. Wait a minute. Yeah, 0 to 5. No, actually, I'm wrong. It's x equals 1 to x equals 5. That is why, my friends, you put this here. Okay, that's how you figure it out. Okay, so that means we're going to go from 1 to 5. And we'll put that in here. And remember, that's right minus left. So right minus left. Okay, so now we found our limits of integration. Now we actually got to do the math part. So we're just going to integrate what's on the inside of the parentheses here. Just treat it as a separate integral problem. But the key with this one is, since we're doing this with respect to y, that means x is going to be treated as a constant, just like the number 4. Just pretend like x is 3, for example. So this would be 4 over 3. So remember, it's a constant. And the derivative of 1 over something, I'm just going to put that, is the the antiderivative of 1 over something is ln of that something. So basic calculus rules here, and that's how we're going to evaluate this. So since 4 over x is like a constant, like a number, it's just going to stay out over here. And the antiderivative of 1 over something is the natural log of that something, which is 1 plus y plus 1, and we're going to evaluate that from y equals 0 to y equals x minus 1. And before I do that, I'm just going to show you what the rest of the notation looks like, I guess. So we would still have our integral here, so this would be dx, and over here we have from 1 to 5. That's our volume. Okay, so I'm going to move that on to the next slide here. So using the fundamental theorem of calculus, we know to take f of b minus f of a. And to do that, we'll just, let's see what that would be. That would be, let's see, derivative, antiderivative, ln x minus 1. That means we plug y in. That means you would just get ln of x. And then when you plug in 0, you would get minus ln of 1. And ln of 1 goes to 0. Oh, forgot the constant. I'm just going to move that over here then. 4 over x. Don't forget the constant, people. And then you have your dx still. Okay, so then we would get this here. Now, to show you what I did exactly, I brought the 4 out just to make math easier for later, because you can't just take the antiderivative of this normally. We're going to actually have to use u sub to make life, I guess, simpler. So you would just get ln of x times 1 over x, and I just brought out the 4. Okay, so that's just what I did. Alright, so now we're going to have to do some u substitution. So I'm just going to think off over here. So I'm going to make u equal ln of x, and du, the derivative of ln of x, is 1 over x dx. Dot bubble. Yay. Okay, so let's try it out. 4 times the integral of u du would be 4u squared over 2. So you add a power and then divide by that power, which would be 2 times the ln, let me see. Yeah, 2 times ln of x, so I'm just plugging u in now to the equation, so that'd be u times ln of x, all that squared, evaluated from 1 to 5. Boom. And we would get, let's see, 2 times ln of 5 squared minus ln of 1 squared. That would go to 0. So our answer would be 2 times ln of 5 squared. That's it. And our units was in inches, and since it's volume, inches cubed of rain. Boom, you just figured out that that year there was 2 times ln to the ln of 5 squared inches of rain. And if you want to know what that number is, that's about 5.181 inches cubed of rain. So remember, since we were only doing it over a small region, which was a triangle, which was a very small triangle if you think about it, that's how much water was in that area over that year. So that's practical use of double derivatives, and there you have it. Keep practicing, guys.